Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. My distinct pleasure to introduce. Ranveer, no jokes. I know my hair is okay. Anyway, distinct pleasure to introduce Albert to you guys. You've already read his bio. I'll just say a few words. He's an AT&T fellow. He's done a lot of work in measurement, network measurements, and network management. Has moved a lot of technology from research into operations at AT&T. He's done a lot of papers. He has managed groups like and people like Jennifer Rexford and company. He's also right now the chair of Sigmetrics, and he graduated from Dartmouth, and then he did his master's and PhD at UW here. So welcome. And
thanks, Victor. Okay, so I'm mic'd up, and this is on, I assume?
Yes, it is.
Okay, so I'm going to talk about some results that had a really big impact in how large service providers operate their networks, and I think they're simple and beautiful results. It turns out that the fundamental thing you need is this traffic matrix, which I'll describe, and I'll talk about that result. And then there's newer work, and I'll talk more about in the area of anomaly detection, which really gets more into the fault monitoring and and a broader set of spaces for beyond just service providers, but many different things. So this is what I'm going to do. I'm going to talk about a problem, or the problem I'm going to talk about in trying to create robust operations of a network. A little bit about the problem, why is it hard, how to approach it, and then I'm going to get into the meat of the talk, this traffic matrix inference stuff, and talk about first and second order statistics. So really the problem of robustness is trying to get to the next 9 in some sense, to make the network more reliable. What roughly it means is that small events, and there are going to be lots of events, are going to have small impact. If you push it a little bit, it's going to move a little bit, not fall over. These events are diverse. There's failures at every layer of the network. There's anomalies in routing. There are attacks going on. There's misconfigurations by operations. There's optical layer glitches that come and go, and there's maintenance. It doesn't seem to really converge, and the reason is that there's software involved everywhere, and the software is changing all the time. So though you may have conquered some fault or misconfiguration type problem today, you'll have to learn about a new one soon because the next release is coming out in 6 weeks. The challenges are you have to support basically everything on IP. Right now, IPTV is big, or all kinds of video on the net, and gaming, and voice and so forth. But just little glitches in the network amplify into huge problems for example, people playing the EverQuest games or people watching TV. So TV doesn't like loss if it's being streamed. And then there's just increasingly stringent requirements from enterprises. If a company like Merrill Lynch is down for an hour, that's millions of dollars of damage to them. The web has to be up all the time. There's no good time for maintenance. Sort of like in Las Vegas, when are you going to have good time for maintenance? Little network glitches have been known. We have customers that tell us at AT&T to trigger large application outages, and then you just make it bigger. So the problem is more service, more infrastructure, lower cost, fewer people, and yet make it more robust. So there are lots of different problems that operations has to chart a course through, but two of the big ones are upgrades and maintenance and faults. So a quick example of how in a network, so when you want to do something like RAID for networks, and the problem is that something small changing in a network can impact things everywhere. So it's less independent than RAID. So here's just one example that I like to talk about because it's a big deal. The example I'm going to talk about happens about 500 times per year to AT&T. So the integrity of an IP link, like between Los Angeles and New York, really depends on this optical network. So this complicated, there's like 10 times more, or 100 times more devices down here in the optical network than in the IP network. And their dependencies, and understanding these dependencies is vital to understanding the integrity of this. And one way to understand the dependencies is through a notion of shared risks. So a shared risk link group is a set of links associated with a given risk. So like if this is a conduit that fiber is running through, then it defines a shared risk link group. So Los Angeles to New York really shares something with San Francisco to Washington. It's that conduit. And about 500 times a year or so, somebody does maintenance on one of these SRLGs. And when that happens, if they take out that conduit, it can be changing an optical amplifier, it could be something that they have to do, then it'll take out those two links. So that's the little local thing having global impact. So how do you cope with this? So there are lots of data inputs that one needs. You need to know the topology of the network at these two layers. You need to know the traffic matrix, where's stuff coming in and going out. You need to know the risk model, what are the dependencies, and the workflow. When is that maintenance going to happen? So you can configure the network to survive the maintenance. And then you need the network model, then you can predict the impact. So what's the hard part? The modeling part, as it turns out here, is not that hard. We know how the protocols work. We can model, we can simulate them, we can predict. Somebody does something at 2 a.m., what's going to happen. But the harder part had to do with managing all the data that flows into the network model. And the surround systems to manage all that data, just think of it, there's 100,000 optical components out there. There's all this workflow happening. There's errors in databases. Getting that part right is data automation and self-cleaning and self-managing, self-everything is hard. And the other hard part, the analytic hard part, which is what I'm going to talk about, was the traffic matrix inference. So what is research about operations? Well, it's not necessarily just operations research, although the flavor of my talk is going to be kind of OR, operations research stuff. It's a much, much bigger sort of ecosystem of things you have to do. And basically, it's about software. So in order to scale something and make it reliable, get to the next 9, one of the things you have to do, which I talked about in the Victor's MSR Summit, is just manage all this data. So automatically. And traditionally, data is kept in these individual silos, databases, with something like a Java interface or a web interface, what have you, that because it's designed for people to interact with these databases. And that's not going to cut it if you want to do network engineering or find problems in networks. So one of the things that we created is a way to, if you want to onboard a new data source, you could describe it in a nice simple form, XML, since XML solves world hunger, and then it would generate all this code, and the code would then create database tables and so forth, and then the data's out out of the silos and in a form that you can now correlate and do automatic fault detection and network engineering with. That's one part of it. Another part of it is updating the network. And this turns out to be it's not enough to know about what to do to the network. You have to have a way to implement that and without any fault itself. So we created a template-driven way to enforce what the architects want to happen to the network or the tool wants to happen to the network, rather than the architects and the engineers writing configuration guidelines, which engineers read and interpret and then script automation. Now, there are components in our data flow, like an Excel spreadsheet, which are there because we realize operations will sometimes need to override, and they need a convenient interface for doing that. So we're not taking people all the way out of the loop. But the main flow is automation. So that's part of the research on operations. Back to the topic, traffic matrix inference. So it's knowing where the traffic is coming from and going to is the most important component to do scientific IP network engineering. We didn't have that before, so we didn't do scientific network engineering before. It was, what are the forecasts for marketing? How do we, a lot of different inputs went into it, but it wasn't good enough to solve that problem I showed you with the guy doing maintenance on a fiber. That was all sort of black magic. But once you have that and you have the other components, you can do in a sound way capacity management, network design, traffic engineering. The key component of that is these first-order statistics. There's an algorithm we have that I'll describe called tomo-gravity, which has been, several papers about. There were several papers before that, and then our papers, and I don't know, 6 or 7 more papers sort of looking at it. But this method gives very accurate traffic matrices, good enough for all that stuff up there in seconds. The second-order statistics come when you're looking at different methods. When you're looking at anomalies or unusual activity in the network, and there we have this method called anomography, and it's joint work with Nick Duffield and Matt Rowan, Yin Zhang. For the most part, there are a few others too.
So how often do you calculate these matrices, and how accurate? How do you know how accurate they are?
We have partial net flow data. The net so the story is that I had really high hopes for net flow. So what net flow is data that describes directly where the traffic is coming from and going to, and it just gets streamed off the routers and so forth. And it's a feature that is part of Cisco iOS, but that doesn't mean you can turn it on. But where we can turn it on, because it doesn't melt the router down or cause other problems, or the feature is actually supported on the interface, then we can get data that helps us to validate this. The other thing is that in operations, they have constantly they're scanning the network using active probes all across the network that tells you what the end-to-end health of the network looks like. And so if you're doing some sort of operation on the network, you're watching that screen. It's like a doctor doing an operation. And you'll see rows go red or something where traffic is now blocked. Then that red will mean that loss is bigger than 80% or something like that. You'll do the operation, finish it up, and you hope it goes green again. Okay. So what we are predicting is when we do these traffic matrices that it's okay to go ahead. You don't have to worry about reconfiguring the network, and things will stay green. Or you have to reconfigure the network going in, do the operation, and then change it back, revert back, and then it'll get green again. So for about 6 months, we sort of simulated this red-green thing. And then in the field, it was also there. So if there was ever a glitch, we would see in operations that the prediction was wrong. So those are the sort of the modeling approach using NetFlow and the in-the-field approach with the active probes is how we validated the idea. Independently, some guys from Level 3 did a study that also validated the idea. Yeah?
NetFlow actually does sampling of data.
Yes.
And it's my understanding that the implementation of that sampling algorithm is different device to device. So how does that factor into your data gathering, or does it?
So you're right. I mean, you can configure NetFlow differently, and there's all NetFlow on the CAT, the switch platform may be working differently, even keeping different fields in the NetFlow record than in the router platform. So when we collect NetFlow, we build a collector infrastructure, distributed infrastructure, server infrastructure, which gathers all this together. It actually does another level of sampling and gives you a uniform record, and then we report back to a central structure.
Do you take into account the business model, the baselining?
Yeah. So what you want to take into account is the accuracy needed. So sampling will create an inaccuracy. So if you're looking for example, certain kind of attacks or security threats, the sampling will get in your way. Or if you're looking to, depending on what you're looking for, you should tune NetFlow differently. What you need is, I mean, it's another topic because I'm not going to be talking much about NetFlow, but what you need is a way to get the most accurate results possible from NetFlow given your computational resources.
I just was curious how you compensated for that in your.
Okay.
So I think you answered my question.
Okay. Cool. So here, the constraints that we are working with, and these are kind of general comments, are the following. So use data that's widely available, ubiquitous data. So I'm here just going to use the link loads, how much traffic, the volume of bytes across interfaces. You can't buy a device pretty much without those link load or utilization measurements from what you'd pick up at Best Buy to $1 million router. The configuration files and forwarding tables are also ubiquitous. But also, if you have NetFlow, if you have better data, if you have Packet Monitor, then why not use that too? So basically, everything's welcome, big tent. But rely on the widely available data. And then achieve accuracy depending on the task that you have to solve. And it should be robust because in the field, bad things happen. So counters run backwards. You lose data. Data gets corrupted. All kinds of things happen. And so if your method depends on accurate data, then it's in trouble. You should expect some defects in your data source. Yeah.
I had something about loss greater than, not loss, link utilization greater than 80%.
Yeah.
Obviously, over what time period? That's not the peak, right? You have,
right.
If you have TCP flows and things like that, you'd often expect it to be running close utilization as part of the normal behavior, right?
Right. Right. So on a 5-minute time period. Yeah. So and it depends on so I'm talking about a backbone network. So we're not going to peg a link for 5 minutes, or we wouldn't want to, on a backbone network.
Here the intent is to over-provision it such that there's no way to utilize it, because we have some new TCP algorithms that actually do try to compensate for some of the things that cause underutilization today.
That's
something that's going to cause red flags down the road.
Well, the sort of assumption is that the bottleneck will be at the edge of the network, before this edge. Yeah. Okay. So it'll be a DSL aggregation router or something else where you'll be able to burst up to that peak. These are OC768. These are big links, and one TCP flow can't really budge, at least not with the current TCP, these links. Maybe with Vista.
In Vista, the things that would be
Okay.
bounded by simply window scaling inefficiencies would go away, and so there would be things that would be transcontinental flows. If a lot of your traffic was meaning across the oceans and stuff,
Right.
then you'd see the underutilization go away for that. And I just want to make sure that if there's assumptions here built in about the normal link utilization must never go above 80%, I don't know if that's going to hold or
Well,
not.
these are just network level objectives that people can use as guides to, as an example. Right. Yeah.
So you mentioned that one of the strikes against net flow was the overhead of turning on net flow on the router.
It's become less so, but
I was wondering, is it an issue even on the edge access routers?
it's it depends. Yeah, some of the edge access routers do a lot of stuff in software, so it can be an issue on them.
But it seems like if you had net flow information from all the access routers, then
Right.
you could then.
Believe me, that was my hope. I mean, when using research money, I bought NetFlow licenses for all of AT&T. Unfortunately, I wasn't able to get full value out of them because in the lab, when we turned it on, bad things happened. We love this stuff. We use it for other purposes like threat detection, but it's not necessarily the right tool for everything. So another way to put it is even today when we have better NetFlow, we still use this stuff because this stuff works and is robust. And so that there wasn't a lot of incentive to re-implement it. Now I'm just going to lightly describe how this technique works. And when I talk about anomaly detection, I'll go into more details. But the one thing you can do right off the bat is if you look at the flows, let's say this red dotted line on top called Route 3, which flows between node 1 and node 2. It goes through two links, link 1 and link 2. And let's see, so that's this third, that means this third route, this third row goes through. So the B's here are the link loads. So B1, let me do the one I've got on the slide. B1 is X2 plus X3. So B is link loads, X is origin destination pairs. So route 2 is this route here, and route 3 is that route there. And so the contribution on this link are from these two routes. So I can write a simple little matrix relationship between these known measurable quantities, B, and the things that I really want, where the traffic is coming from and going to, the X's. And this is the routing matrix, which I can compute from forwarding tables and configuration files. So I can pose the problem as a matrix problem. I want the X's, I've got the B's, and if I can invert this matrix, then I'm done. The problem is that it's a massively under-constrained system with lots and lots of solutions. So it's like saying if I told you the traffic on every road in Seattle, now you tell me where the cars are coming from and going to. There are lots of solutions. So this had been kicking around for a while, and how can you try to solve it? You can just try inverting that matrix. You can try something called gravity modeling, which I'll describe. You can try something called network tomography, which I'll describe. And then these other two things, which actually work a lot better. So I'm going to show a bunch of these graphs. So this is from a validation. This is the here I've got the real traffic matrix value, and here I've got the what you can infer. So if I just try to invert the matrix using MATLAB, this is what happens. So if I get it right, it lies right on this line, and this is the 20% offline. And pretty much the data is all over the place, somehow all concentrated there at the origin. It didn't work at all. I can try what's called gravity modeling, which is a simple idea that's used a lot in planes, trains, and automobiles, and world trade and other things, which is just saying that just if I know how much one site is producing and how much another site is consuming, then the flow from this producer to that consumer is proportional to those two volumes. And that leads quickly to some simple equations about the aggregates flowing out of each site. It doesn't take into account any of the internal constraints at all. It just looks at the aggregates out of the sites. If I do that, then it gets a little better, but it's still not good enough to use for anything. Another idea that came up, actually, some statisticians at Rutgers and Berkeley and so forth proposed network tomography, where you could get additional constraints if I assume something about the statistical nature of the flow between sites. So I could say, oh, it's a Poisson random variable, and they're uncorrelated between the sites. That leads to a lot of additional constraints, which then helps me to solve the problem. But on the other hand, they were only able to solve problems of about 5 sites or so, and that doesn't work when you have hundreds of sites, and the statistical assumptions are all violated in practice. So when people looked into it, it didn't work. People from Sprint. This is the first thing that we used, actually. So I didn't really know what a gravity model was, and this is the first thing I came up with, and it's what we used. But then later when we learned about gravity models, we called it the generalized gravity model. So this took into account everything I knew about routing. So in the internet, routing is asymmetric. So you've got links and routers in different roles. You've got your access and you've got your peers. And typically, let's say you're in Seattle, and you send a packet to Yahoo, then it'll want to get out of, let's say, using Comcast network as quickly as possible to get to Yahoo. And that quickly as possible stuff is called closest exit or hot potato. So I can create a gravity model, take into account as much as possible that I know about routing, because I know that routing is going to have a big impact on flow of traffic, obviously. And I get the generalized gravity model. And that starts to look good enough that you can do some network design with it. And that's what we did before we had something better. But it really wasn't good enough for a lot of operational tasks, like there's a maintenance going to happen tonight, and will I be able to survive it or not? Or will I have to do some last-minute engineering to survive it? After bashing our heads at this for a while, it turns out there's a simple solution. And it's called tomo-gravity, and here's how it works. So first, there's all kinds of tricks we can do with the topology to reduce the problem size. So that matrix is a very sparse matrix, the routing matrix, and there are extra constraints or redundant constraints that can be removed. Do that. Then compute the generalized gravity solution. Think of it as this point in this little space. And then if I think about all the other data I've got, this is all my data and all my constraints, just walk over to the closest solution feasible to the generalized gravity solution. And you're done. That's tomo-gravity. We have to define closest. So the obvious thing to do is to use a least squares approach, closest in the least squares sense. Why is every sort of matrix element created equal? Aren't the large ones more important? Yes, they are. So you somehow use a weighted least squares, and yes. And so we tried various things, and certain kind of square root weights work best in practice. So that's what gets used is weighted least squares with square root weights.
What's the intuition behind that?
I'm coming to that. So when we thought weighted least squares would be better than just least squares, because some traffic matrix elements are more important, the large ones, but we didn't know what weighting function would be best. It turned out that, so we were giving this talk, actually Matt Rowan giving this talk at Dartmouth, and David Donahoe was in the audience, and he said, "Oh, I know why square weights work." And then he sort of pointed out this foundation for the method in information theory. So we actually just came up with it, and then Donahoe, interacting with us, came up with why it's the right method from an information theoretic point of view. So the foundation is called minimizing mutual information, and it's sort of the maximal entropy type principle. Let's not make any unwarranted assumptions. Let's keep uncertainty at a high value. Let's not assume things we're not sure of. So define the information gain, I of SD is the information gained about source S from destination D, and don't assume any further information except for those given by your constraints, your measurements. And then the gravity model just is assuming independence between what's happening at S and what's happening at D. But they're not really independent, because I know that there's routing involved. So take into account all that routing stuff, and I get conditional independence. And then when I formulate this and I try to minimize the mutual information, then I get exactly the same computation, except instead of the weighted least squares, I get I use this special Kuhlbach-Liebler divergence, which measures difference between distributions, probability distributions, and do some manipulations, and to first order, I get back my weighted least squares. So I guess the moral is that if you look at things from the right information theory point of view, what tomo-gravity pops out is the first order approximation. And then when we did experiments comparing the full thing to the first order approximation, there was nothing to choose between the two. So you might as well use the first order approximation. So now the accuracy starts to look good. Everything lies in this wedge, and the large flows are really good. And the large flows are the ones that can really saturate links. So they're the most important. How does it track over time? The actuals and the estimated track quite well over time. Where there is a difference, at least they have the same shape, and they're following the same kind of patterns. I don't want to go into the details of this graph, but what I'm doing here is I'm injecting noise in the data. And the blue line is the original prediction, and these other lines are what I get when I inject more and more noise. And again, I'm making defects in the data, and small defects lead to small changes in the result, which is what you're looking for. And it's okay to lose data, things like that, because if you lose it in one place, it's going to be measured someplace else, and the least squares is going to pick it up. If I had...
Something about data cleaning. Don't you have a data cleaning module before?
Yes. I do have some data cleaning before, but the result of that is I might have missing data.
This is not wrong data, this is missing data. You said
I'll have some wrong data occasionally, too. I mean, but not... counters will turn over, and the algorithm will make a mistake about 3 turnovers in a row or other sort of corner cases. If I've got net flow data, especially if I can choose where I can collect the net flow data, I can do much better. So here, with these dashed lines, I'm choosing where I'm collecting the net flow data on, and a net flow collection could give me a whole row of the traffic matrix for free. So if I have 20 rows, for example, for free, then I can do less than 2% error.
This is pretty underfunded.
Sorry?
This is 20 out of how many?
20 out of about 100. Yeah.
I don't quite understand. How do you get the entire row from one net flow collection point?
Well, a row is, in this sense, is telling me for one source, where's all the traffic going, all the different destinations. So if I'm measuring net flow around the entire POP, or all around a router, all the interfaces of one router, then that would tell me where all the traffic is going to if I'm measuring at that router.
Assuming that's the router at the source. I mean,
Right. So, or out of. I can either get a row or a column.
if you measure some router in the middle of the network, that's not
Right. Then I won't. Yeah. Then I'll get some. Yeah. Right. That's all I'll get. Yeah. Another idea is I can get more constraints from just keeping a few extra variables in each router. So George Varghese proposed just knowing, inside the router what the traffic matrix is, how much goes, out of interface 1 to interface 6 and out of interface 2 to interface 7, those little local matrices. And it turns out that a similar kind of graph, that if I have, what's happened here is that the graph has moved to the left because the local traffic matrices made things a lot more accurate. So the real story is that with a small number of local traffic matrices, I can again drive the error down to a few percent. So the bottom line is this stuff works. It's used 24/7 at AT&T. This impact analysis is in the fabric of operations. They won't touch a fiber or a router or something without checking the impact through this technique. It uses the widely available data. It's accurate enough for the task at hand. And you can improve the accuracy, and other people looking at it have found that it also works. One fortunate thing is that you don't really want the traffic matrix. You want to know what will happen to the network given a traffic matrix. Like if I cut a link and the network reconverges, what's going to be the new loads and all the links? And that's a much lower dimensional problem. So if this is an n-squared dimension problem, that's an order n dimension problem, where n is the number of links. And the accuracy is much, much better for the application than for the traffic matrix. And somehow the errors are canceling in a nice way. So there's been a couple of papers about that. So the predictions you can make based on this stuff turn out to be more accurate through this aggregation than the inputs. Okay, and I'm going to go on now to the second order statistics, and that regards unusual conditions called anomalies. And they can come from distributed denial of service attacks, flash crowds, misconfigurations, outages, and so forth. You want to diagnose that quickly and fix the problem. So what you typically want to do is you want to know, has there been an unusual event? What's the best explanation for it? And so what? Should we call the CEO? Should we just write it out? How big is it? And then of course you go on and mitigate it. The focus of this part, the focus of my talk, is just detecting these anomalies. So here's an illustration from a paper by Anukul, very nice paper, Lakina. So if here's the original flow between origin and destination, say this flow here, and there's an anomaly in it, well, it's going to show up in these little bumps on the individual constituent links. So I'm going to be monitoring these individual links, and all these little bumps are happening all the time, right? But I want to pick out these cases where the little bumps add up to be a significant change in the network. a change in the traffic. And that's the problem. So I'm going to use the same mathematical framework. Nothing's changed there, just the traffic is doing, the x's and the b's are doing new things. I can rewrite that now explicitly taking time into account, because I'm looking at anomalies in time. And I can rewrite it again by keeping a window of time together. So now b is a vector of those b sub t's, and x is a vector of the x sub t's. And I'm going to assume for now that the routing is not changing. That's not true. Routing changes. So I'll come back to that. The contribution here is something called network anomography. And it's a very large class of methods. And it spans a wide range of different time series analysis techniques and inference techniques. So you can pick your favorite time series analysis technique. You can pick wavelets if you like wavelets, or ARIMA. That's what you have code for and you're comfortable with, and so forth. And also we'll tell you how these different things stack up with one another. It includes all the previously known techniques, including the nice technique called the subspace method based on principal component analysis that Lakina introduced. But it also quickly leads you to some new and better techniques that are more accurate and more robust. So how do we go about this anomaly detection? There are two steps, and there's inversion and anomaly extraction. And you can do them in two different orders. So let's call the early inverse, where I do the inversion first. So I was just raving about how great this tomo-gravity stuff is, so why not use it? Why not? I measure these BTs, these link loads, and now I want to infer the origin-destination flows. I just use tomo-gravity to invert from the B's, given the A, which can also depend on time, and I'll get my X. And then I'll do that across time, and I'll get a bunch of different OD flows, inferred ones, called X tilde. Tilde will mean inferred here, or sorry, anomalous here. And then I'll just run whatever anomaly extractor I want on these OD flows. And that'll give me my anomalies, X tilde. So that's the natural thing to do. We had high hopes for that. But it had, we tried it, it had big problems. So the first is that this inversion step introduces systematic error. The reason is it's doing some sort of least squared fitting or curve fitting. So if you've got anomalies, like they tend to be concentrated on with a small number of causes, but the method is going to smooth out the causes and attribute them to a lot of different candidate causes. So it's going to not find good explanations for big anomalies. That's one problem with it. The other problem is you're doing anomaly detection on the OD flows. There are lots of OD flows. There are fewer link load measurements. So you're doing anomaly detection in a very high dimensional space. Well, let's look at it differently then. Let's do the anomaly extraction first and then do inversion. So I'll just look at my measurements, look at my link loads, B, and I'll extract their anomalies. That's nice, low dimensional, and there are lots of ways I can do that. And now I can throw in my constraints and do an inversion to go from the detected anomalies to that tilde should be on that X to the inferred OD flow anomalies in the last step. That's called late inverse. Okay, so let's look at late inverse because it does work better. So how can I go about it? Well, basically I'm measuring these link loads B, and I want to forecast from a given link load measurement what I expect the link to be looking like at the next instance. So I can use any forecasting method I like. I can just use ARIMA. So I can use the simple thing that I forecast the future to be the same as today, or tomorrow to be the same as today. Or I could use an exponentially weighted moving average, or I could use a more sophisticated, higher order method like Holt-Winters that takes into account the diurnal fluctuations and so forth. And that's one class of methods. And so once I've got my forecast F, I can just subtract that from the observable, and that's the anomaly. So the difference between the forecast and the observed is the anomaly. I can use Fourier analysis, in which case the low order coefficients describe the normal behavior, and I take the high order coefficients as anomalous behavior. I can do principal component analysis, which is the technique that Nuka Lakina and company introduced, and I can do that in two ways. This is the way that they did it. We call Spatial Pca, which is works on the rows. So in Spatial Pca, the idea is that there's correlation structure between the rows. So if one, I expect that there's a diurnal pattern that describes what should be happening on all the rows, unless there's some event, in which case they all should change together. So the rows themselves are correlated. And what that should mean is that really this data should collapse. There should be a small, a smaller sort of system that should describe the collapsed joint behavior of all the links. That not every link is unique. They all sort of look alike. There's an average link behavior, if you will, which will be the first component in PCA. So the idea is to look at the data and collapse the dimensionality so that you can describe the links in terms of this average behavior. And then that's called, what you get is, through that analysis, something called the normal subspace, the normal behavior, the big sort of large-scale behavior of all the links. So to find anomalies, you project your data into the normal, into the complement of the normal subspace called the anomalous subspace, which should be all the energy that looks different than normal. And then once you've quantified that energy, you transform it back to the original coordinate system, and you've got your anomalies. You can do that one instant in time for all the links, or you can do it for all the links together for all instants in time, which is what these guys did. So one thing that comes to mind right away when you formulate these things is it self-consistent? So if I had net flow data, if I had complete knowledge, and I was just monitoring the OD flows directly, and I was applying my anomaly detection technique directly, would I get the same result with that same anomaly detection technique applied to the observables that I am in reality able to monitor? And if that's true, then you get this self-consistency equation that basically is saying that the anomalies get routed too. So if B equals AX was true for normal traffic, then it's going to be true for anomalous traffic too. And all of the temporal approaches I mentioned can be modeled with right multiplying transforms. And it turns out that they all come out to be self-consistent, which is a nice fact. But it's not true for the spatial approach. So for spatial PCA, you can detect anomalies that just can't happen, or the opposite, that you can fail to detect anomalies that do happen if you were to measure the flows directly. So one reason that this happens is that the spatial PCA method is insensitive to the time series. So it just if I take all my data and permute time and run spatial PCA, I get the same result. So if you think about like anomalous behavior, like it goes flat for a while, then it ramps up, and it drops back down, you might say that's anomalous, right? But I could invert that. I could take that flat part and move it to the right, and then it looks like, so I take the right part where it dropped back down and move it to the left, and it just stay down, flat, go up. There's nothing anomalous. But the Spatial Pca doesn't care about that. So, I mean, there are cases where you use the PCA method that, I don't know, recognizing faces and trying to find a known face and a sea of faces that's time independent, and it works well. But when there's time involved, I think you should be cautious about using it.
These are observations you made after that paper was published?
Yeah, that's right. Yeah.
And,
Yeah. I mean, the paper got us excited about the problem. That paper got us excited about the problem, and then another Donahoe paper got us excited about the problem. But the Donahoe paper was this more stat paper about sparsity, which I'll talk about here. So after we've extracted anomalies, we have to do this inversion step. And I've talked about tomo-gravity, and one defect to do inversion of that method and other methods that for inversion is they all have to have a prior to work, like the gravity model or something that makes sense to work well. But when you're looking for anomalies, you really have no idea what the prior should be. So what should you try? And so this Donahoe paper and other papers on sparsity maximization suggests that, and this fits intuition, that if there are lots of explanations, pick the smallest number of explanations that fit the data. And we sort of think that makes sense, that there's like a DOS attack on this website, or there's a popular content here, or for whatever reason, Hotmail just went out and traffic has dropped. It's like one explanation for anomalous traffic, not 1,000. And if you're looking for that, you take that approach called sparsity maximization, then the formulation that's usually led to is, if I've got all these possible contributions, then try to minimize the ones that I choose to explain the data. That's going to be minimizing the number of non-zero elements in the solution. The trouble is that this is a really hard computational problem. But it can be, you can pick another norm, which is just the sum of the absolute values of the explanations, and now you get a tractable problem. And that's what the Donahoe paper was about. That there are lots of cases where, when you're trying to solve this, if you solve that instead, you get the same solution. You pick the same explanations. That technique for inversion we call sparsity L1. There are other techniques, sort of a greedy technique for keeping adding possible solutions until you fit most of the data, and then stop. That's almost all of it. The final bit is that you have to be robust. So routing will change. So when routing changes, that'll change the structure of the traffic on the links, because now it's being routed on different links. Typically you monitor routing with routing monitors. So you don't need a traffic monitor to tell you that routing changed. And you don't want the thing that's monitoring traffic to tell you traffic changed when in fact routing changed. And so you don't want to throw away your data when routing changes, all this stuff. So you want to be robust to routing changes. Another thing is, beyond just routing changes, you may lose some link load measurements, and that is equivalent to how it hits the linear algebra to a routing change. So you want to deal with that too. The early inverse method, which I said doesn't work so well, carries over directly to handle routing changes. This late inverse method has some issues with it, but if you use the recursive approach, like exponential weighted moving average or any ARIMA approach, then you can basically carry through the recursions so that the fact that AT will be different than AT plus 1 and so forth, you have to keep all these T's around doesn't hurt you, and the method just ports right over. So now I'll get to evaluation. So there are these two steps, there's anomaly extraction and inversion, and I'll analyze them separately. So let's look at inversion first. So fix a anomaly extraction method, let's say the diff one, where you just predict that the next period of time will be, or you forecast the next period of time will be the same as the previous. Then I'll compare all my different inference methods from that same anomaly extraction method. And I use data from the Abilene network and a tier 1 ISP. I looked at the real, where I had net flow data, OD flow data, and inferred the link data by the technique. And I measure goodness by this thing called detection rate. So I look at the top in real anomalies and compare them to the top in inferred anomalies. So it's good to be up there at the top at 1. That's 100% overlap, which is what I'm looking for. And all of the different techniques, this sparsity L1 technique works the best. This is, again, the most parsimonious explanation for the anomaly. When I look at different ways to handle routing changes, again, sparsity L1 works better than the other technique. Now I need to evaluate the anomaly detection method. So again, I'm going to use partial net flow data. So I'm going to compute IM anomalies by applying anomaly extraction directly on my net flow measurement or OD flow measurement, and I will also infer anomalies from the link data. And now I'm going to look for overlap between the benchmarks and the inferred data, and look for false negatives and false positives. And I'll choose these parameters similar to the amount of anomalies that we expect people to actually want to chase down per week, say 30 or 50 or so. Here's what I get. So the payoff of the consistency, the self-consistency stuff, is these diagonals are zero, are essentially zero. So these are the different techniques I can use for the time series analysis up there. And because the methods are self-consistent, that if what I detect in the inferred agrees with what I detect in the OD flows. The overlap and the agreement between all these methods is really good. So they all sort of detect the same, pretty much the same 50 or so anomalies, 50 or so biggest anomalies, whereas the PCA methods don't work so well. And the reason they don't work so well is really we're looking at big anomalies. The big anomalies get confused as normal traffic in the PCA approach. They're big enough to not get separated out as anomalies. And the other thing is it's a least squares type method, and it's not going to look for these unusual explanations. It's going to smear the power out around many explanations. So it can be good at picking up the little bumps. It's just bad at picking up the big bumps. I'll skip that. So the bottom line is that this anomography method also works. We looked at many different possible ways to implement it. We found this one that is simple to implement, handles routing change, has a low rate of false positives and negatives. There's various parameters in the numerical fitting that deal with errors. You can't solve the equations exactly, so you have a penalty term. How you parameterize that doesn't really matter in a broad range. And it can, if you have NetFlow data or other data sources, then you can accommodate that in the framework. So this method also seems very practical.
Question?
Yeah.
Go back to the previous slide. So step one is applied on the linked load information.
Yes.
So I thought one of the basic problems was that if you looked at the linked load, you wouldn't really see any anomaly, but then it could add up and the OD flows there would be an anomaly. So I'm just wondering how that would work. I mean, step one might be nothing.
Well, you'll. Good point. Let me think. You will see I mean, you keep all the data. You keep the difference between forecast and prediction. So you're not going to be weeding out the top end after doing the ARIMA step or the step one. So you retain all the original data. It's all there having an impact. It's not being thresholded. Okay. It's not till the very end where you do I'll take the top end. There's other applications. I'll just mention a couple from other people. So I think there's a lot of mileage in the anomography stuff, and people are applying it. So the one is I talked about, trying to compute traffic matrix using tomo-gravity, and I can accommodate NetFlow data, but what's the best way to combine SNMP data and NetFlow data? And there's a paper about how to do that, where first you basically run anomography to do a kind of anomaly detection to find examples of data that really doesn't make any sense, and those are basically wrong data. And so you run anomography, then you smooth out the data, and then you run this tomo-gravity using both data sources, and that does better than just tomo-gravity alone. So they looked at using some NetFlow measurement, and they could cut the error substantially using this technique. There's Yin Zhang student Song came up with this technique called NetQuest, where he applies this to another tomography problem, which is you're scanning across large networks. Actually, AT&T does this to find performance problems in the interior. The trouble is, if you've got in probes to scan from, you've got in squared flows, and that's a lot of data for out at the edge of the network where you have thousands of sites. So how can you collect something that's just as good using fewer probes? And so what they do is they use a Bayesian approach to select where to put the measurements, take into account the amount of overlap you're going to see in the middle. Then they use anomography to do inference from the measurements they do collect, and then they infer things like path delay from the result. So it's pretty amazing. They can probe only 5% of the pairs in a big network and infer what they would see on all the others with good accuracy. There is other work going on related to this and larger set of problems, which I published in other papers, and as I said, it's going on. Knowing what the anomalies are in traffic or routing are just part of the problem. So in order to do fault diagnosis, usually you have to slam lots of data together. And that's when you really see the root cause. So there are good reasons for traffic to go up and down that really you should not react to as a problem in operations, or raise a ticket or cause a tool to do something. And it's only through the correlation that you pick that stuff up. So other data sources that you can correlate with are BGP routing, router CPU, for example. So once given that correlation, you can do much more and much improved decision support. The other thing is automated response. So if you found a problem, maybe the anomaly was an attack, and you want to scrub the attack packets out of the network, for example, then you need tools to automate that, make it happen in the network. And there are lots of different knobs you can twist to update the network. But the issue is you must have much less uncertainty about your data sources and the problem when you go and update the network automatically. This leads to it's like a Pandora's box. It leads to a whole wide set of projects to clean up the network, to prepare for automation, and then a set of mechanisms that go and change routing configuration to do something to fix the network. That's my talk.
Okay, thank you very much. Yes, we've already asked some questions, but in case anybody has, this may be the time, or not.
So I want to go back way at the beginning. You talked about the Presto system.
Yeah.
So how successful has that been? Like, can you tell me how deployed that is? How long it's been deployed?
That's a good story. We invented Presto for IPsec VPN management, and after inventing it, they did it by hand because there were so many different devices out there, and it was changing, and the need wasn't strong enough. And then it sat there for a while. And then only in the last year or two did the problem come up again, provisioning customer edge routers. So now you've got a customer like USDA or somebody like that has 10,000 sites or something. And they're not exactly cookie cutter. And there are lots of options for each site and so forth. So there was a real scale problem to enable those kind of customers. So that's when the opportunity for Presto came back. And so that's where also we could see, so like if there's a 1% chance of making an error and you're just doing 100 routers, so what? But if you're doing tens of thousands, now you're starting to see real errors and real pissed off customers. So we had real examples of that now out in the field. So that gave us sort of the mandate from basically the customer care executives who are paying to have all this stuff purchased but not making money, and dealing with to go and implement Presto. So we went big with it this year, and we learned a ton about inserting automation in a manual process from that experience, because the way a big customer was enabled in the past would be an order would come in for 10,000 routers or something like that to a lead enabler, and he would create some templates and then tell 15 people, you do the hubs, you guys do the spokes and so forth. The Presto technology obviated all of that. We didn't need that. And so it changed roles of customer care and roles of operations. And the other thing that we found is that, and so that we had to overcome those issues, is that the engineering rules for how to configure those routers were just guidelines. And the guys that wrote them were great architects and so forth, but the guys that implemented them were talking to customers. And the customers would say, if you implement it that way, I'm not going to buy the service because I know that won't work. And that wasn't necessarily getting back to the designers. So the operations guys had become really smart and they knew things that the designers didn't know. And so the engineering guidelines were not that great. So part of the exercise actually was a new discovery of what the right rules were and put the right people in the driver's seat to configure these templates. And that actually, sort of from a human point of view, won over the support of the ops guys because they are the ones that really knew the right templates and so forth, and they were part of the template drawing team. So I mean, there were things like something like the password of last resort. And so in the US, that was used for everything. And in EMEA or something was used as the password of last resort. There are all these sort of different conventions that were implemented differently around the world. And so all that got straightened out this year. So once we did it for this one huge service, now it's been reapplied for the VoIP service. And there's about people clamoring to have it applied for the backbone router, just the backbone routers that we deploy. We only have a few hundred of them, but they have to be done right when they're being replaced. We happen to be replacing them this year to the next generation. So I think the idea was great when it was first created, but the real need to go big with it wasn't until this year.
Okay, thank you. That's good.
Thanks.